class we will discuss about magnetic field due to current carrying a circular coil. So we will discuss some special cases here. Okay, and now here I will take the first one. If x is very larger or greater than a. So in the previous lecture we have discussed all about the magnetic field along the axis. Is that right? So we find out the magnetic field at the point P there. Okay, and now in similar way here, if I had considered if x is very much greater or else larger than a means, right now just by seeing this figure you will get it very easily. If I had considered the circular coil, okay, which is carrying the current I, okay, and now here already we know that this is what the x and this is the radius of a coil A here. Is that right? And now already what we know here, x is very greater than A here. Okay, so due to that reason already we got the expression for the magnetic field. Is that right? That is B is equals to mu naught by 4 pi into 2 m by a square plus x square to the power 3 by 2. And already we know that this is the magnetic dipole moment. Is that right? And now I can write this one as the IA. I is the current carrying the circular coil and A is the what? Area. Okay. And now here, if you substitute that one means that is mu naught. This is to the okay mu naught by 2 pi NIA by a square plus x square to the power 3 by 2. Is that right? And now here, let us see here, already what we know that x is greater than a. So I can rewrite this expression like this. This is mu naught by, and you may substitute like this. This is what already we know that pi a square, pi it cancels, okay, and now you are remaining with mu naught by 2 n I a square whole divided by this is what x square. Is that right? And now here why I had considered this one as the x square only, because a is a very least as compared to the x here. So finally we got the expression like this. This is mu naught by 2 into NIA square by 2x square. Is that right? So I can write this one as B is inversely proportional to the x square. Is that right? Okay. There is a small method just to look at here. What we are having here, x square to the power 3 by 2 is there. I can write this one as the x cube. So that's why it will be x cube. Okay. And now here, so what we got it here, this magnetic field which is inversely proportional to the 1 by x cube. And right now this here, it will be similarly behaves like an electrical dipole moment also. How? So I can write this one as, see, I can write it here, electric dipole moment, as like already we know that E is inversely proportional to the what? X cube. And even the similarly what we got it here, when x is larger than a means, here also we got it here, B is inversely proportional to the 1 by x cube. And instead of this, if I had written this one as inversely proportional to the x square means what it will be? This is for what? Point charge 1 by x square. Okay, already we studied all these things, electric dipole moments. Okay, so now this is what the in the case of x is very larger than the a. Okay, and now here in the similar way I will go with that another case. What is that case means? Magnetic field due to C at the point of center. Here what we are having, in the previous lecture I showed it here somewhere, just I had taken the very finite x here. I could say this one as infinite also, no problem for this case. If I had considered initially, as I said in the previous lecture, that is P, what I had taken this point, I had taken that point in the center of this circular coil. Is that right? Is that right? And now here, for this I had considered the radius as the R, okay, and even the whatever you can consider this one as the small element dl. Is that right? And now this is what the current I, okay. And with respect to that, just to look at here, so with respect to this I can consider the angle theta, and from this what we are getting it here, angle is 90 degree, and which is always 90 degree for this case. Is that right? Because at this point here you are going to find the magnetic field. Is that right? And now here this is the point P, okay, and now at the point P, I can write this one as dB is equals to mu naught by 4 pi. You are going to use the main tool, that is the Biot-Savart's law. Is that right? Mu naught by 4 pi ideal sin theta by r square. Okay, and now already we know that the theta is 90 degrees equal 1. Okay, and finally we are remaining with dV is equals to mu naught by 4 pi into ideal by r square. Okay, and now here, right now what I am going to consider, just I had considered the only small element. Is that right? And right now if I am going to find for the whole circular coil, means at that moment what you have to do, just you need to integrate on both sides. What you will get it here, that is after integration, on both sides, we have, for that equation, B is equals to mu naught by 4 pi, take the constant parameters both sides, and I by r square. And for the whole circular coil I had considered this one as the circular closed circular path, okay, that is I can write this one as the dl. And already we know that the resultant for this integration is what we are having, 2 by r. Radius is here I had considered this one as the r. That's it. And now r get cancels. Is that right? And now here and write b is equals to mu naught, and even though 2 pi get cancelled, 2 2's are mu naught I by 2r. This is what the final expression, magnetic field due to current carrying a circular coil at the point P at the center of this circular coil. Okay, that is B is equals to mu naught I by 2r. Okay, and you may write like this also, no problem, or B is equals to n mu naught I by 2r. Here what that n indicates, the number of turns which is related to this circular coil. That's it. Okay, and this is what and the special case towards this concept. Okay, and in the similar way I will consider the another one, that is somewhat we can call it one as also a case also. In this circular coil, the magnetic field is uniform or not an uniform. Okay, just we need to understand that concept. Okay, so just to look at here, I will show you. Here I will consider this one as the C. For example, if I had considered the circular coil, okay, so now here for this I will consider the point X. Okay, this is the point P, similar way, and even though I will consider along the negative axis also. Okay, so that is minus X plus, okay, that will shows you the both the directions, okay. And now already we know that the current carrying the circular coil I, okay. You may consider the length element, no need of considering any small element or like that, okay. And now here I will show you this one by graphically. How you are going to show that one? If I had placed the bar magnet north and south pole, and already you know that the right hand rules, okay, as I said it in the previous case, with the first case, in this case what it will shows you, that will shows you the direction, in which direction you are having the magnetic field. For example, just to look at this figure, just you see here, if I had considered the right hand, with respect to that the current is flowing like this, is that right? This is the center point, okay. Here I am going to find the magnetic field. For example, this is the circular coil, and right now here in this circular coil I am going to find the magnetic field, okay. So in this moment what I have to do here, this is the right hand, now I will place it here, just to consider this is the center point, okay. And now these four fingers, what that will show you, current is flowing around this circular coil, okay. And now what is the direction of the magnetic field? It will be, what it will shows you, see here, this is the outward direction, is that right? Okay, so that's why we may use the RHR, that is what the right hand rule, okay. In the similar way here also, if I had considered like this, means what it will shows you, the anti-clockwise direction, is that right? Okay, for example, right now just to look at here, you will get very easy. See here, for the north pole, what it will shows you, it will be anti-clockwise direction, and in the similar way, if you consider the south pole means, so with respect to that, what it will shows you, it will shows you clockwise direction, is that right? If there is a presence of any magnetic material, with respect to that there must be existence of two poles, okay. You should not able to explain only north, only south, okay. And even though we could not able to separate those two, there must be existence of those two poles. And in the similar way, if I had placed the bar magnet in center of the circular coil, means how it will behaves, okay. For example, if you want to find the magnetic field intensity towards this circular coil, means how it will shows you graphically, I can write like this, see here, I think it will shows you very significantly. Just to look at here, I can consider this one as the magnetic field, is that right? And now I can show like this, is that right? So this is, see here, along this direction it will be minimum, and even though just to look at here also minimum, and here what you are having, it is having the maximum magnetic intensity of the magnetic field. Here it will be max, and here it will be minimum, is that right? So from this, what we got it here, if you went away from this circular coil, the magnetic field intensity, it will be decreases, okay. It will be very in the minimum, okay. And in the similar way, if you come near to this circular coil, the magnetic field intensity, it will be in the extreme position, that is what the maximum, okay. So it seems to be having the same curve also, okay. And now here, see here, graphically I can represent like this, is that right? Magnetic field intensity, is that right? Which is the maximum at this point, and which is the minimum at these both points, okay. So from this, what we are going to conclude here, no uniformity, there is no uniformity towards the magnetic field in this case. This is what the conclusion, okay. So this is what all about the special cases which is related with this magnetic field due to current carrying the circular coil. Okay, so thank you. So in the next class we will go with the next concept, which is problems which is related to the previous classes. Okay, thank you.